Alright, in yesterday we talked about the Kirov-Argyle paradox and proving that the femboy need not be gay, or the definition of a femboy is independent from the definition of being gay. Now today, we will be discussing about the Stefferson-Maxwell paradox. I talked about, I sort of implied in the previous week that I'd be talking about the Stefferson-Maxwell paradox, and well, today I'm going to talk about that. So before I discuss the this paradox, the Stefferson-Maxwell paradox, first I'm gonna need to discuss, or I'm really gonna need you guys to watch the previous video or the Banach-Tarski video by Vsauce. Um, the Banach-Tarski paradox by Vsauce. He discussed about it and proving that we can decompose a ball in such a way wherein we can rearrange those pieces into two copies of that ball, right? By essentially duplicating it. And in the paper concerning the Banach-Tarski paradox, the author gave a stronger version of the Banach-Tarski paradox by saying that through this paradox, through that theorem, and the Banach-Schroeder-Bernstein theorem, we can say that two bounded sets are congruent via equidecomposability. So in essence, we can prove that a set A is equal to B under equidecomposability. But before we actually discuss that, before we actually discuss the paradox over the theorem, I'm going to need to discuss the Banach-Schroeder-Bernstein theorem, the Banach-Tarski paradox as well, before we go into that. I'm only going to be discussing the proof of the Banach-Schroeder-Bernstein theorem. The proof for the Banach-Tarski paradox is already there on the in Vsauce's video. The entire video is essentially explaining it in a simplified manner, and also Wikipedia page is full of that stuff. The paradox, the construction of the paradox, and the proof of the paradox is in the Wikipedia page for it. So, right, Banach-Schroeder-Bernstein theorem 3. We listed as theorem number. The previous one we have theorem E, theorem 1. Theorem number. Suppose a group G acts on X on a set X, and if any set, any of the two subsets A, B, subsets of G on the X are G, capital G, equidecomposable with the other. So when we say that if B is a subset of X and it is G decomposable with A, we can say that the vice versa is likely. A is G decomposable with B. And when we say that these two are G decomposable, they are equivalent under G, under the group G. And the proof for that, proof for this theorem, so we're essentially saying if we have two sets, so if we have two sets, let's say the Yowie set and the femboy set, and we have some external set, some universal set, which does not exist, but rather they are both contained within that set, and some other action is acted upon that set, we can say that the Yowie set and the femboy set are equivalent under that action we perform on the set they're part of. So, alright, the proof for this is that, alright, so consider the G decomposition as maps. So let's consider the decomposition as alpha acting on A, or alpha maps A onto alpha acting on A, which is a subset of B, and another one, B acting on, well, beta acting on B, or maps B onto beta on B, subset of. Okay, let let A sub 1 equals some intersection from I equals 0 to infinity of alpha, beta combined, acting sub I, or to the I, acting on A without interacting on B. Because we know that this is part of A, we just sort of minus it. Let A sub 1 be that. Since now since beta acting on alpha acting on A is a subset of beta acting on B, which is a subset. I'd say proper subset with that with the mark on the bottom because they cannot compose the entire thing. Which is a subset of A sub 1. We have by induction, we can say that alpha, we can say by induction that B act, beta acting on alpha sub I or to the I, beta acting on alpha to the I is an acting on A is a proper subset of. Yeah. So A sub 1 is a proper subset of. Okay. Erase this for 1. So we have space. Alright. Okay. Let A sub 2 be A sub 1, A minus the set A sub 1. And let B sub 2 be B sub 1. B sub 1. B alpha acting on A sub 1 subset, proper subset of B. And B sub 2 be this or be B without this set. B sub 1. Sub 1. Alright. Now, next, we must note that A sub 1 is equal to A minus beta acting on B union beta acting on alpha acting on A. So A sub 2 is equal to beta acting on B intersection A minus beta acting on alpha acting on A1. And then that goes to, that's all that equals to, it goes on and on until we get beta acting on B sub 2. So, thus we can construct a G equidecomposition of A and B by removing, let's just remove A from A sub 2, from A sub 2. A sub 1 is a subset of A sub 2, of course. But let's remove that, or we cut it away, and perform alpha, or the mapping, on A sub 1, and the reverse map of beta sub 1, or beta to the negative 1, on A sub 2, to get that G equidecomposition, and say that these two sets A, B, are equivalent under G. Alright, that proof was very heavy, contained a lot of math, so really, I suggest that you guys feel yourself before we begin with this course. So, that. Next, we have theorem 4, which is the Stefferson-Maxwell Paradox. We can say that a set psi is equidecomposable with two copies of itself.
So I'm gonna leave the proof of this to you guys as an exercise. It may require the axiom of choice and some other things. But really,
The proof is also there in the Banach-Tarski paradox here by Vsauce. It's in the description in the previous video.
and using this theorem, theorem 4, and the Banach-Schroeder-Bernstein theorem and some induction, we have theorem 5, which is the
Stefferson-Maxwell paradox, named after Milo Stefferson and Max Michael.
theorem number 5, the Stefferson-Maxwell paradox. The bounded
Non-empty set, non-empty
transgender set P is equidecomposable with the femboid set. With
P and F being subsets of R3, where R3 is just the three-dimensional number system or real numbers. And now the proof of this theorem lies within the using of theorem number 4 and 3. And so, all right, this one's gonna be a bit of this one. So I suggest you guys steer yourselves. All right. Proof. Okay. Using the Banach-Schroeder-Bernstein theorem, we can show that A is equidecomposable with a subset of B and vice versa.
So we can say that P is decomposable with F, with a subset of F. And vice versa. Okay,
Let's assume that M is an open set, inside, open set or subset within T or F. I'm gonna say F. Using the Banach-Tarski paradox and induction, we can show, or using the Banach-Tarski paradox and induction, M is equidecomposable with a finite number of itself. And so, using these finite numbers of M, or say that M is equal to basically some numbers of itself, we can fill T up with these copies of M to essentially show that F is equal to T. Right? So, since F and T are bounded, we can position these finite copies of M such that they compose A. Hence, A is a disjoint union of M, of M, or these copies of M, and is equidecomposable with the free image in D of the subset under the topic proceeding. So there's a proof. So after this, and then some stuff, I'm saying that, and filling T with M, filling T with M with subset of, we can say that F is equal to T, because The subsets of M compose F,
and we're saying that the copies of M are equal to just one copy, and we're fitting these copies inside T to say that T is equal to F. So, by def, T is equal to F under equidecomposability.